Hello, everyone. I'm very glad to follow Professor Punekar. Congratulations to him for this award. Uh, this first award of today is recognizing dissemination of knowledge, scientific knowledge earned, learned through several years for the benefit of a vast majority of people. This award, the second award, is a Young Researcher Award. So, an award for a young person who is taking off on his career. And I'm very glad to be present here on behalf of the Department of Earth Sciences to introduce Dr. Vikram Vishal, who is a faculty member here in our department since 2016. He was actually a student of ours in our department and passed out in 2009. And incidentally, he was a classmate of Professor Punekar's daughter, who is also our faculty member. So you can see that there's a lot of things going on in this in IIT, where we have a very senior professor and a professor who is now just getting into the process of research and so on. Uh, Professor Vishal was initially a faculty member in IIT Roorkee, from where he went for a Fulbright fellowship to Stanford, where he worked on petroleum geomechanics, reservoir geomechanics, and then he came here and joined in 2019. And from then, he has been instrumental in developing the experimental geomechanics laboratory of our department. And his principal interests are in reservoir geomechanics, in carbon sequestration, and in enhanced oil recovery. So these are the main research interests of Professor Vikram Vishal. But in these few years from 2009 onwards, he has been prolific in his work. He has won 2 national awards, one from the Ministry of Earth Sciences and one from the Ministry of Mines. And he has also earned recognition from all three academies of India, scientific academies of India. And so he's been a prolific worker and therefore a very promising faculty member for our department. He also co-authored one of the big achievements of his is that he co-authored a book which is called the Carbon Capture, Utilization and Storage Roadmap of India, which was released by the Government of India in July 2018. So Professor Vishal has a number of students and he has a vast network of contacts with the industry, and he has been forging ahead with his research interests. In addition to all that, he is also now a member of some of the important committees, particularly on enhanced oil recovery, which has been set up by the Government of India. So there is a very promising career and a promising future ahead, and let us spare a few minutes to listen to what he has to say.
Thank you, Professor Pandey, for the very nice introduction. Actually, a teacher. So it's always nice to have a teacher introduce you in a forum. Again, back to IIT, where I was a student myself, and right now a faculty. So I take you from the enzymes that are presently active, as Professor Punegar introduced us to some of these enzymes that were active millions and billions of years ago, when these plants and animal life were supported, and they ended up becoming fossils and fossil fuels, what we are presently using for all the our requirements of energy. So these fossil fuels include natural gas, coal, and oil. So the very first slide that I put here is to make a point that with the projection that we have right now and what we are currently using, the fossil fuels are here to stay, essentially oil, natural gas, and coal. So do you know when the sustainable development concept was trusted since the 80s? What was the percentage of fossil fuels in the energy mix? Any idea? It was 81% back then. So what our target was to reduce fossil fuels in the energy mix and have a more sustainable development which is friendly with the environment. Do you know what is the percentage of fossil fuels in the energy mix right now in the world? It's still 81%. So we are still using the fossil fuels. There have been debates on how we'll transition from this to the renewables. That's the aim actually. We want to move on from the fossil fuels and target more on the renewables. But my point is that fossil fuels are here to stay essentially. So what happens when we are burning these fossil fuels? Essentially coal, because India is predominantly, our energy is supported by coal, oil, and natural gas. So we are releasing large quantities of carbon dioxide. This anthropogenic carbon dioxide is being added into the atmosphere that we are living in right now. So from the historic ice records that we see from right now to 160 thousands of years before present. So you see, whenever there has been a CO2 concentration rise in the atmosphere, it has been followed by a temperature rise. So there are many evidences which support the CO2, as you all know, is a greenhouse gas and supports the global warming that is affecting our planet as a whole. But what is to be noted that in the human history, at least when we have lived, the concentration of CO2 was not above 280 parts per million in the atmosphere. However, right now it is the Keeling curve which has been mapping the CO2 emissions in the past 60 years or so, and right now we have crossed 417 parts per million. Most of it has been emitted during the last 150 years. So that's a kind of a consequence of industrialization that has been supported by use of fossil fuels. So then fossil fuels are definitely required because we need to support the development, we need to have more and more energy security, but at the same time we need to be more responsible as a global citizen and find out efforts to mitigate the direct impacts of carbon dioxide in the atmosphere. So one of the methods that have been identified for capturing this carbon dioxide and storing it is by what we call as geologic carbon sequestration. So what we do essentially in this, we find out these large point sources of CO2 emissions, like these power plants, all the other industries that emit CO2. We can capture the CO2 from these power plants and compress them, transport it through pipelines to locations where we can store them, and inject it down, deep down into the subsurface. The analogy for this is that the natural gas and oil that was formed millions of years ago has remained trapped into these reservoirs. So that's the analogy. We want to put the CO2 and not release it into the atmosphere, but rather put it down into the subsurface. So my research involves along this condition where the reservoir is interacting with carbon dioxide. So this fluid interaction with the substrate is what I work on, and I'd like to talk to you about that, but also mention in the topic something about the unconventional. So this is a resource pyramid which kind of lists the conventional and unconventional sources. There's a difference of conventional traditional from your, you can understand, these are the reservoirs that we have been tapping oil and gas for, for almost 1.5 centuries or so. And they have been pretty well understood, and we have done good understanding on this around the world. So this is top of the pyramid here. But as we go down the pyramid, we have these unconventional hydrocarbon sources such as shale gas, coal-bed methane, gas hydrates. So the incentive here is that the volume of oil and gas that is present in the deep, in these unconventionals is very high. So that can actually support our energy requirements for the future. So our energy security is enhanced if we tap more of this. However, the challenges are many. You see, this is the unit of permeability. So the permeability that is 100 millidarcy. So permeability is nothing but the ability of the substrate to pass fluid through it. So once the fluid is passing conveniently, we can recover more and more oil and gas. But here the permeability is extremely low. So what the target is to enhance the permeability from these reservoirs and get the oil and gas. But at the same time, we don't want to disturb the overall system that is there, so the system integrity becomes important. So this is from example from the US natural gas. We all know about the shale gas revolution of the US. So after natural gas was increased in the energy mix, so this is the natural gas production is increasing, the CO2 emissions overall has come down. So moving from coal to natural gas is actually helping us with less amount of CO2 emissions. So that's an incentive, another way of looking at it. So these are the three questions that primarily our group focuses on. They are parts of reservoir geomechanics. So to understand what is the pore space, so what is the volume of that gas that is present. So when we talk about percentage recovery from these reservoirs, we must understand what is the numerator and the denominator in that percentage. So numerator we can figure out because whatever gas is coming out is in the numerator, but denominator is the what is the total gas that is present. Now, because these systems are new, not much have been studied, so our group focuses on kind of devising the protocols through which we can understand these subsurface better and kind of give those better estimates of these gas capacities and the subsurface. And then what's the ease of extraction, that is the permeability and the system integrity strength, because once we are taking out the oil and gas, we are definitely altering the pore pressure and stress conditions internally, and that is linked to the stability and integrity of the system. These are the three questions which we try to address. So this unconventional revolution, as we call it, so this has more energy, this has less carbon, and then there is a proposition that once we have removed the natural gas from these systems, we can use the same pore spaces which have become voids to inject the carbon dioxide and store the carbon dioxide. Okay, so this is a small animation because we all know about hydraulic fracturing. This is by the courtesy of Baker Bridges. I just wanted to show that how we actually hydraulic fracture. So last 2 decades there has been development of this hydraulic fracturing and horizontal drilling. And see, this is the horizontal drill well. This is the target species where we want to extract the gas from. But these formations are extremely tight, so the gas doesn't flow. So we need to create fractures so that these pores get connected. So this high pressure propellant and fluid that is flowing through this tube, it's called as a ball and sleeve mechanism. So and this blocks the other part, and this high pressure that leads to fracture. And in kind of these sockets and sleeves, from one part to the other, we go from one, it's like the heel end of the reservoir to the toe end, and in a series, we kind of go on fracturing. So now, in our group, we try to generate these conditions in the lab, creating that high pressure, that high temperature, and see what kind of rock behaves in what way. So every system within, from basin to basin, and from within the basin, from layer to layer, these beds are different, the conditions are different. So a better understanding will be needed to exploit these reservoirs. So this is a glimpse of some of the facilities that we have in our lab. So we go to the field. This is, of course, an open cast mine, which is just for representation purpose. But we also get deep drill samples from hundreds of meters deep, in some cases kilometers deep. We get those samples from these oil and gas companies that are working, and then we create this subsurface condition in the lab. And you have this hydraulic stresses from the sides, the stresses inside the sample because of the fluid that is present. Then the temperature is controlled, so pretty much replicating the subsurface. And then we have just for permeability, gas absorption system, and another gas permeability compression system machine that's for deformation. So as the three questions that I posed, pore volume, permeability, and system integrity, we address all of these in our lab, and of course we do some numerical simulation as well. What essentially happens, because of this fluid, they are at high pressure temperature. The phase of the fluid also is different. So at the normal PT, it's like a gas, but deep down there, they become supercritical, liquid, and then supercritical. So supercritical fluid has different behavior as compared to subcritical. So again, most of the studies that have been done before are focused on powder samples and in gas phase of the compound, whatever it's methane or CO2. But our aim is to understand how the gas behaves in the subsurface conditions. So for coal, the talk is in four parts. One is coal, shale gas, and gas hydrates. The principles are still surrounding around the geomechanics of these reservoirs. They are all unconventional. So we take these coal samples, we put them into one of these systems that we can replicate the conditions, and then we see how it is deforming, how it is allowing the fluid to flow from one end to the other. And these become inputs for the model that we generate for having regional scale mapping of the gas productivity. So we have these kind of regional scale model. This is only for representation. You have a CO2 injection well, so we inject the carbon dioxide. This carbon dioxide essentially drives out additional methane. There are different reasons for that. First of all, coal has high absorption affinity for CO2 over methane. So it takes up the carbon dioxide and pushes out extra methane. So it's driving out extra methane. So we have enhanced methane recovery. So by primary recovery, we can get around 25 to 30% of the methane. But by secondary recovery, using carbon dioxide, we can get up to 50% more methane. So this is solving both our problems. We are injecting CO2 inside. At the same time, we are producing more methane, which is needed for the energy security. So, for a simple representative purpose, this is from one of the Raniganj basin in eastern India, and you can see that if there was no CO2 injection, this trend would have followed somewhere like this. However, because of the CO2 that is being injected in the central well, it's driving out extra methane, and that kind of changes the trend from here to in this direction. So we are getting a big quantity of methane produced. So this has been proposed, and we are working closely with SR that's operating the wells out there. So our studies are being meaningful for their lab works, for their field works as well. Coming to the problem of shale gas, the gas that is stored is in extremely fine nanopores. These nanopores in pore dimensions, which having diameter of around 0.6 nanometers. Most of the studies before have focused on pore diameters above 4 nanometers. Some of the studies went to 1.6 nanometers. But we changed the experimental protocols and kind of using primarily the VET analysis, we found out the pores that were not primarily reported in the range of 0.6 to 1.2 nanometers. Now the point is, all those pores that were not accounted in all these estimates that have been done previously. So once we assume that these pores are 100% saturated with methane or natural gas, so automatically the denominator that I was talking about in the percentage recovery, that gets changed. So the estimates that have been done with older protocols. New protocols are being set up, and then now we are getting a better understanding of these subsurface. So this is Sondergaard figure. This is a well bore, and as you go from scale, this is a decreasing scale. So the fluid flow here is along the fractures, mostly Darcian, then slippage, diffusion, sorption, and drumming. So we want to understand these systems better so that we can have a better understanding of it. So in that case, we are using FEXM that's available in IITB, LPGA. We are also using few other techniques also. That's the low pressure gas option. What you see here that by simple one protocol, that's the outgassing procedure. We change the temperature of outgassing from 100 degrees. So typically researchers would use 110 degrees to eliminate the water that was present. But we change the temperature from 100 to 250 degrees Celsius, not altering the overall structure of the substrate that is present. Using the PGDDA, we could map that. And now we find out that there is additional amount. So the volume that is present here is much higher than what was done before. Simply by changing the temperature as of the outgassing of the system. So using different protocols, we are trying to find out what is the gas estimate. Using PEX and image analysis also, we're trying to find out those pores, map their volume, and give the kind of correlate with the other method and figure out and give the exact numbers of the volumes of gas that we find. As I showed you this tracking experiment, the animation, so we kind of generate that in the lab and replicate the same for the simulation, and that gives a better understanding of the reservoir while we are exploiting the reservoir. So essentially, our protocols talk about outgas temperatures, the DFT models, so QSDFT, NLDFT, density functional theory models, and as well as the absorbent model. Basically, shale has silica, shale has carbon. Theoretically, it's assumed that carbon is where we have most of this natural gas, but also clay can absorb significant amount of natural gas. So because clay absorbs, so that also has to be accounted for. So we are proposing that we have to stitch the pores that are seen in a carbon model and that are seen in silica model, and adding them on together, we can get a better estimate of the gases that are present. So collectively, we are doing these studies for understanding the shale system. So on the pore size, pore size and pore volume estimation. At the same time, by simulating the hydraulic fracture. So what are the pressures that are needed that can create a fracture, but not be long enough to propagate into another strata? Otherwise, if we create fracture that can go up to a larger distance, in that case the oil and gas or the gas that is present can leak and go into another formation. That is something that is not desired. So that control is also developed by simulation studies. Another aspect of our studies is to understand methane hydrate bearing sediments. So if you know, in 2014 or 2015, there was an announcement, a big discovery that happened was all along the offshore of India. We found out huge gas deposits. So these are essentially gas hydrate deposits. They look something like this. So unlike other phases where gas is present as the methane is present as gas or liquid, here it is present as a solid form. Essentially, there is water, and water is frozen, and it has a large amount of gas trapped in it. So a conventional system can have one volume of gas in per unit of per unit rock volume. An unconventional system like shale can have 7 to 10 times. Gas hydrate system for a unit volume, it can have nearly 150 to 170 volumes of gas methane. So if you tap the same volume of gas hydrate, you have much more amount of methane that comes out that can solve. So what is said that even 10% of exploiting this gas hydrate in our offshore, we can fuel the country for 200 years. So that's the challenge. But the challenge is that's the incentive. But the challenge is that all around the world, nowhere we are producing gas hydrates, the gas from the gas hydrate system. So that's a challenge. But India having huge reserves, almost 963 trillion cubic feet of methane is present in the eastern offshore of India. So that's the incentive. We can extract more and more natural gas. So in our lab, what we are doing two things. One is to stimulate the underground conditions that are present and use a combination of depressurization and heating so that we can enhance the methane production. At the same time, we are building up a lab facility. It's not installed yet, but we did a trial experiment from where we are purchasing, and there we created again the subsurface condition and created different hydrate saturations and allowed us to help us to understand in what PT conditions we can dissociate the gas at the same time maintain the stability. Because these systems are so fragile, if you have taken out the gas, essentially you have distorted the solid that was present. Unlike in other cases where the gas was in pores, in this case the gas itself is a solid matrix. So that is what is supporting the entire system. So once you have dissociated the gas, you have essentially made the entire system fluid. So that's the biggest challenge of gas hydrate. So we replicated the conditions in the lab, and we are trying to measure or rather optimize the depressurization and heat dissociation so that we can still maintain the stability of the system and extract methane gas. So in this work, we basically had a permeability data from the experiment and we validated it through a model. And this is the model that we can use for a regional scale mapping of the gas production. All right. So the point here is you can find oil in a new place using an old idea. But if you're looking at the old place and still you want more oil, you don't really get it with an old idea. You need more new ideas. So that's how we are pretty much looking into this subject of phoromechanics and trying to resolve this for the unconventional systems. So we have gone beyond, and we are in collaboration with ERC. We are using their small angle neutron scattering system. So essentially in that case, it's a non-destructive tool. At the same time, we can, through this method, we can measure the connected as well as the non-connected ports, and that's another, so that will give another incentive to understand these systems better. And this is from the CT scan that we have facility in SAF here, and essentially we are scanning the entire block, finding out the distribution of ports and solids in the system here, and we are splitting it into matrix blocks and the port block, core unit, and within the ports, what are connected, so the green ones are connected and the red ones are the non-connected ports. So to that level, when we are talking about reservoir exploitation in kilometer scale, we have to look at something at nanometer scale to understand how we can understand the system better. So that's the focus in our lab, and some of the findings have been published, and the students are essentially working on this right now. So coming towards the end, so what are the future opportunities of the unconventional? We are talking about the CO2 problem. At the same time, we are talking about more requirement for methane and natural gas and use of fossil fuels. So what I see as a proposition, India has not really done any of these work on CO2 storage in the underground. I mean, on the site, this is confined to the lab. But what I see as one of the major areas of research right now is injecting the CO2 into the subsurface and go towards a pilot or demonstration. This is a map of India. Here, these big black dots are the large point sources of emissions of CO2, and we are working on a Mission Innovation Carbon Capture Challenge project where we are trying to map the nearby reservoirs where we can capture the CO2 from these large point sources and inject it in a very nearby vicinity reservoir. So we're finding those reservoirs out and mapping and injecting, proposing for injection of CO2 out there. So, of course, if you look at the theoretical capacity of the CO2 storage, it's very high, but we have with more certainty and matching, the capacity becomes less. So, but then we need a better estimate at this level so that we can give a proposal to these companies where we can see CO2 storage happening in India. So this is my concluding remarks here. So basically significant potential exists. So that's what our group focuses on, with reservoir mechanics for unconventional. So with renewed gas capacity estimates, we are using our protocol to propose these renewed gas capacity estimates for India. Because if USGS has a number which is so different from what the Indian Geological Survey would have. So that's why our protocol becomes important. So the CO2 enhanced oil and gas recovery solves like two problems together. One, it provides us with energy security with extra methane and addresses the problem of climate change mitigation by injecting the CO2 inside. So this is from the IEA, which shows that of all the efforts that are needed for controlling the temperature rise of the globe to less than 1.5 degrees Celsius, 32% of all that effort has to be CCS, that's carbon capture and storage. So that's the seriousness of CCS around the world, and that's what it is needed in India as well. So again, towards the close, this looks like a numerical simulation, right, to most of you. It looks like it's very easy to make a numerical simulation, but it actually is not. You can see here basically something is being injected here, it's rising here, and the concentration is growing. Essentially, this is how oil and gas remains trapped or confined. When there's a cap rock on the top, it has extremely low permeability, so the oil and gas gets trapped here. But this is essentially a carbon storage model that we developed in a lab, inspired by Professor Markham in Switzerland. And here we are trying to demonstrate how we can inject CO2 at the base of the target formation, and it rises by its buoyancy. It gets trapped at the cap rock, which has low permeability, and it is expected to remain there like forever. I mean, typically in geological time scale, forever. So this was needed because most of my interaction with the policymakers and non-specialists, it was a big challenge to understand where are these spaces, so where the CO2 would be stored. Because safety is a major concern, and it should be a concern. But the better understanding of the systems allows us to plan for the safe and secure disposal of CO2. So that's what we built in our lab to explain carbon capture and carbon storage. And it can be, you can visit our lab and see how this works. And this is it should be an animation to show CO2 being injected and coming up there. And this actually led to the interaction with the government, and we came up with this carbon capture utilization storage roadmap for India that was released by DST. in 2018. And this gives us a roadmap that large-scale mitigation of CO2 can only happen once we are injecting this CO2 into these reservoirs. There are options and suggestions, recommendations for forming green chemicals and other bio-based capture. However, the large-scale mitigation can be supported by injecting this into depleted oil and gas formation. So there are different support that I've got from, and I want to thank all of them. And this is my group that has been working and supporting the work that the vision that I have with the Reservoir Foundation. I thank you all for your kind attention.